Good morning, ladies and gents. Chance for us to do a little bit of feedback on the foundation paper here for you. Well done for all your efforts and preparation in the mocks. I can see from a lot of you that you've put in a lot of effort in terms of your revision, and even when you're getting answers wrong, I can see that you are putting in effort and that you're talking about stuff you've learned in science, which is good. You're not leaving stuff blank. So let's get started. I'll try and make sure that you can see the mark scheme, so you don't have to sit and listen to me for absolutely everything. Drawing the lines you've seen for the first question there. Most people were doing absolutely fine on a chunk of this. It was possible that people missed that they've not got a funnel for question 1.2 here to improve it. It's just filter paper sitting in it. You would spot that quite easily. Evaporate and condense was quite commonly answered here, but easy mistakes. Percentage in this one for question 1.4 was literally just a case of counting up. There's 2 the grey ones and there's 20 white ones, and then that's 10%. Always do show your workings out in your science exams, because then if you do make any sort of mistakes, you can at least get credit and score some of the marks, because you've shown how to work out percentage even if you've got the wrong numbers. Mixtures of metals are alloys. 1.6. When you've got that distorted layer, they're no longer able to slide over each other, which means that it's much harder and stronger. So the hardness comes because the layers are distorted by those different sized atoms. At 1.7, if you got it wrong, it's going to be because you did something like add them together. You didn't times them all together. So it's for a volume, it's the length times the width times the height. So that's 20 times 20 times 20. Do use a calculator, ladies and gents. But otherwise, question 1 wasn't too shocking, really, for anyone that was having a look at this. It's good work. Question 2 then. Number of electrons in bromine. It's group 7, it's halogen. So obviously, the answer should be 7 there. Structure for hydrogen bromide. So hydrogen, non-metal, bromine, non-metal. So non-metal is covalent. The right answer being small molecule is a little bit tricky in this one, because it's simple covalent. It's a small molecular covalent. It's not giant covalent like diamond or graphite. The formula for fluorine gas is going to be F2 with a little 2 at the bottom. This one right here, you want to avoid ever putting that for a molecule, F with a 2 floating up at the top. That's for where charge goes. All of the halogens are diatomic. They are so Cl2, Br2, I2, At2. And 2.4. This one needs just a couple of points then to explain it. Everyone's saying that the reactivity is decreasing down the group pretty much, which is true. So chlorine is the most reactive, iodine is the least reactive. Always make sure you get a statement like that. But it does say explain how you know this. So you could say something like chlorine has reacted both with bromine and iodine. Sorry, bromide and iodide. I should get that right, being a chemistry teacher. Whereas bromine only reacts with iodide, and iodine does not react with anything. Okay, you can see why you can get all the marks from on the side here, but you do need that explanation using the reaction as to why chlorine is top dog, bromine is middle, and iodine is at the bottom, not doing anything special. Okay. Whenever you're doing about halogens and their halides, just remember that that element ends in "ene" and that the compound or the ion ends in "ide." That does commonly cost marks at some point. Nice easy one here. When we're looking at relative atomic masses, remember when I've said you get an AR and it gives you these things, then you just need to add those up. Now it's TiO2, so it's a titanium 48, and it's 2 oxygens 32, so combined that should be 80. All right. For a percentage yield, they've given you a range of numbers here just to make it a little bit harder. So what we were predicting was 1.2 kilos. What we got was 900 grams. Those units aren't the same. So for me, I would say that is 0.9 kilos out of an expected 1.2 kilos, or you could have done it the other way around. That's 900 out of 1,200 grams. Now, as soon as you start setting it out, you did a test, 900 out of 1,200 or 0.9 out of 1.2, that gives you 75%. Okay. let's have a little squiz through to number 3 then. So I think there were people getting this wrong, and I think some of you thought that you were only using each word once in some occasions. So just draw you to the command bit. Always read all the bit of the questions in full. This one here says each word may be used once, more than once, or not at all. Okay, so do read that so that you know that you might need to use the same word multiple times. So the center of the atom is called the nucleus. 2 types of particles in the center of the atom are the proton and the neutron. Chadwick discovered the existence of the neutron, which is the last discovery in our little timeline. Niels Bohr suggested that particles orbit the center of the atom. This type of particle is called the electron. And the 2 types of particle with the same mass are the neutron and the proton. So we actually use neutron twice there in a row. I was very impressed with the maths here for the relative abundance, 63.6. They gave you the formula. The formula looks scary, but most people that have a stab at that manage to do that. All it's asking you to do is find the percentage of each. So in this, what we did using that formula was find out what 70% of 63 is, and find out what 30% of 65 is, and added them up. Okay, that should get us 63.5. If you ever struggle at those, you know, you can do the maths sort of like this. When you're looking at isotope 2 here and you need to find 30% of it, so 10% is 6.5, and then you get 3 lots of the 6.5, which is 19.5, and then you'd add that 19.5 onto 7 lots of 6.5. Okay, you do use a calculator in your exams. I know some people, I can see long multiplication and division happening. You need to use calculators, please, ladies and gents. Okay, 3.3 then. Looking at the periodic table, in the help sheet that you got with you, should have led you to copper. It's the one with 63.6. Okay, if you got the first part wrong and you chose a different element based on that, you still get the mark right. Slightly cheeky one here, then obviously we need to know that the atom is about 10,000, so the nucleus is about 10,000 times smaller than the atom. So it said the radius of the atom is 1.2 times 10 to the 10. Calculate the radius of the center of the atom of element X. So we need to make something that's 10,000 times smaller than that. Give your answer in standard form. The way I'd look at doing this is converting your 10,000 times smaller into standard form. So that's going to have 1, 2, 3, 4 zeros. So it's going to be 10 to the minus 4. Like it says here, 1 times 10 to the minus 4. And then you're going to combine those together. So you've got 1.2 times 10 to the minus 10 for the size that's given in the question here. And you're going to be making it 10,000 times smaller. So you're going to be moving that decimal place 4 times. And that 10 and 4 make minus 14. It should be a smaller number. So it should have a bigger indices there, a bigger negative number. Because that's, as that goes up, it's making it smaller and smaller and smaller. Number 4 we did, yeah. So this one was reading off the measuring cylinder. I don't think many people, if any, fell for reading it the wrong way around because it's inverted, it's upside down. You're not measuring the black stuff, you're measuring the white bubbles from the top, and that was fine, 3.6. This one, so directly proportional is a maths term that we need to be familiar with. You're definitely going to need to know it much more when you look at your forces unit 2 in physics. So directly proportional means that it will not only be a straight line graph, but it also passes through the origin through 0, 0. In this case, that is the hydrogen line only. So chlorine is proportional after 8 minutes, but it's not directly proportional. Directly proportional means that there's only 2 terms in it, so it'll go through 0, 0. On 4.3 then, it says, which lines show a positive correlation? Well, they both show positive correlations. Positive correlations mean that it has a positive gradient. It is increasing, starting bottom left, going to up top right. And a correlation means there is a pattern there. They've both got a steady pattern, and it is both a positive gradient. 4.4 then, why can graphite conduct electricity? It's the delocalized electrons. Graphite's got 3 covalent bonds out of potential 4, so there's an electron that's unpaired. And on 4.5, we were looking here at simple electrolysis, so this didn't need any complicated rules. So we were splitting zinc chloride into zinc and chlorine. So zinc is a metal. All metals form positive ions, and positive ions would get attracted to the negative electrode. Okay, so you should have got zinc and chlorine. If you got them the wrong way round, you could get 1 mark for knowing the products, even though you got obviously got the charges wrong and which one they're getting sent to. So well worth guessing, because splitting zinc chloride into zinc and chlorine, nice and straightforward. Next one is not potassium and bromine, because potassium is too reactive to come out into a solution. If you imagine we put potassium in water, it would start floating, fizzing, setting fire with a lilac flame. So it is the hydrogen that comes out. So that was a relatively tricky one to put in the foundation paper. So don't be in any way disheartened if you got that wrong. Electrolysis is tricky enough as it is. And obviously, if you got hydrogen and bromine the wrong way around, you'd be fine. If anyone wrote chloride or bromide, look, it says there, do not accept chloride or bromide, because you are starting off with the compound, the ide, and you're producing the element, the ene. So that is one of the occasions where you do need to get that word correct. Okay, slightly tricky stuff there. And number 5, always get something in an exam where you're looking at either writing a set of instructions or interpreting stuff. There's always some of this how science works bits. There's definitely a chunk in your revision guides which looks at science skills like this, and it's definitely worth looking at those, not just going straight to pure content. So the state symbol shows that carbon dioxide, if you look at the state symbol here, CO2, and it's got a G for a gas, so you need to say gas there. And for 5.2, why do the contents of the test tube lose mass in the investigation? The gas escapes, carbon dioxide escapes. Just look out, when it says things like don't accept references to evaporation, because that's not really what's happening. It's a new product that's forming. It's a chemical reaction. It's not a change of state because you just heated it up. For 5.3, calculate the mean mass in table 4. So in table 4 here, looking for the mean mass, you've got 3 numbers here. None of them stand out as being anomalous results. So add them all up, divide them by 3. If one of those numbers was really, really stupid looking, then you'd want to leave that one out and add the other 2 up and divide it by 2. Okay. 5.4 is the one where they're asking you about an anomalous result in this case. Which result is anomalous? So out of the pattern here, you're looking and thinking, right, all these 3 here, 1.29, 1.27, 1.31, they are all around a similar value, very close to the final mean. If you're looking at this one, the final mean is 2.58. This answer here is 2.89. That's actually quite significantly different than 2.57 and 2.59. And that mean there has been calculated by just using trial 2 and trial 3 and not including trial 1. Trial 1 there for the 4 grams is the wrong answer. Is the anomalous answer. So it'd be at 4 grams for trial 1. How could we make sure that the reaction is completed? Well, if the reaction hasn't finished, what you need to do is keep heating it and then keep weighing it until the mass doesn't change anymore. So the mass is going to be decreasing, decreasing, decreasing until it no longer changes anymore. That's when it's finished reacting. There are always alternatives to things like this, like in the mark scheme here, it says continue heating and pass through lime water until the lime water stops bubbling. That's just testing for carbon dioxide, so it's saying until no more carbon dioxide is given off, and then the reaction will be done. So looking at your graph here, you had a line of best fit, a line of best fit to draw in. When you're drawing your line of best fit in this case, it is an absolute straight line with a ruler going through all those points. It is a nice straightforward one. Okay, do remember though that sometimes we do have curved lines of best fit in science where you drew a smooth curve as close to as many points as possible. For 5.7, it says determine the mass of magnesium oxide produced by 8.4 grams of magnesium carbonate. I'd expect to see some working on the graph here where you go to 8. If that one there is 9, 8.4 is going to be 2 squares across, not 4 squares. So we're going to go 2 little squares across, then you're going to go up to your line, and then you're going to go across. If you're doing that right. I'm just looking at my screen now. That should be pretty much about 4 grams of magnesium oxide. And obviously, if you did 4 little notches along, that would cost you the mark in this one, but wouldn't cost you the mark in the next one. If you use the wrong answer to then start your calculation for 5.8, then you would get the right answer. So in this one here, it says we're going to calculate the mass of magnesium oxide produced when 1.68 grams of magnesium carbonate is heated. So we need to work out, well, how much bigger is it? So the way I would do this, it's not the way that necessarily everyone would do it. So you got 8.4 grams. So if you divided by 8.4 to get it down to what 1 gram would be, and then times it by 168 to get it what 168 grams would be, that'd be our final answer. So you get your starting answer from question 5.7, divide it by 8.4 to find out what it is per 1 gram, and then times it by 168, and that would give you what it is for 168 grams of it. So it's dead similar to doing percentages. You work with percentages in maths in a very similar way. On number 6, again, more how science work questions, knowing things like dependent, independent, reliable, repeatable, really important for your exams. So dependent variables are what you are measuring. They are the outcome of the investigation, so they're usually the blank part of the table at the start of the investigation. At this point, they will investigate the temperature change. The independent variable is what you are changing, what you are investigating. So you usually know this. It's usually the left-hand column on the results table. For example, you're going up in, when you're doing the pondweed thing in biology, is to go every 10 centimeters for the light or something like that. You know that at the start I'm going to go 10, 20, 30, 40, 50. And in this case, they were changing the type of metal. So they knew which metal combinations they would have. I've started doing an answer for a question, you didn't do it. Ignore this. Question 6 wasn't on your test. It's not going to harm you that. I'm just going to scroll past it because it's got all the energy changes stuff that we're doing at the moment. Question 7 was on your test, but it was labelled as question 6, so please don't get confused by that. There we go. So complete the word equation. It is a word equation, so you want sodium and oxygen would make the word sodium oxide. You are allowed to write the symbols for it in word equations, even though it asks for a word equation, but you have to get it right. So in this case, you have to know it's Na2O rather than just NaO. So when it asks for a word equation, do just write the words. What type of reaction is it? Well, it's adding oxygen, so it's oxidation. Hopefully you see the sense there. And when you have a metal oxides are things that will react with acids. So if you notice, 1 and 4 is acidic, so we're going to rule those out. 7 is neutral, so the only thing which is on the alkaline side of the scale there is 13, so that's the only possible answer it could be for something that would react with the acids. So usually metals form basic compounds, and its non-metals form acidic. Let's have a little look. 7.4 or your 6.4. Naming NaOH, that is very, very common in terms of acids and alkalis. That is sodium hydroxide. So obviously when you put sodium in water and it floats and it fizzes and it melts into a ball, it produces sodium hydroxide, a strong alkali, hence them being called alkali metals. It's not the metal that's alkaline, it's the solution that's produced at the end of the chemical reaction. The formula that you'd be hopefully choosing between is between the H plus and the OH minus, because they're the ones that are involved in acids and alkalis. It is the OH minus for an alkali, for sodium hydroxide, and the clue there is it's NaOH. H plus ions are for acids. And for this last one here, a calculation one from our quantitative chemistry. I know this is not a huge fan point for us. First thing, we've got grams per decimeter cubed, and we've got 25 centimeters cubed. We just need to convert those. So when it says grams per decimeters cubed, that is, there's 40 grams in a litre. Okay, so how many litres is 250 centimeters cubed, or 250 millilitres? That's a quarter of a litre. So that is 250 divided by 1,000 to convert it, because it's metric. That'd be 0.25 for a quarter of a litre. So if you've got 40 grams in a whole litre and you want to know what a quarter of a litre is, then you need to just divide that by 4. Okay. Obviously, the calculation for that, the formula for that is the volume. There is the concentration. Sorry, the volume divided by the concentration. concentration divided by volume there. Sorry, get myself worked out here. We're doing the maths. So it's how many times would that fit in, and it's 10 grams, which is a quarter of 40. Okay. 7.7. You are plotting a graph based on these values here. So the only thing to make sure is that you get the atomic number and the melting point on the right lines. Pretty well done for most people. The only problem that you get there is when you draw in a line of best fit, did it ask for a line of best fit? No, it just asks for plotting it. That's why it's only 2 marks. When it asks you to predict the melting point of X, the unknown thing, then obviously what you're going to do is you're going to get atomic number 37, atomic number 35, 6, 7, and then you're going to go up and roughly look around where it should be, and you should get something around 39 degrees Celsius if you're looking in between the other points. And obviously because you're sort of guesstimating here, it should be anywhere between 34 and 46 are reasonable guesses according to the exam board. And you did this one here, number 8. So give one other type of substance that can be reacted with an acid to form soluble salt. So it says at the top, soluble salts are formed by reacting metal oxides with acids. So you can't say a metal oxide, and you can't name a metal oxide. But what you can do is say pretty much anything else. So a metals react with acids. A metal hydroxide, like we discussed earlier, like sodium hydroxide, is a very common one for that. Any metal carbonate, like sodium carbonate, other metals exist, or even saying an alkali. For 8.2, which I think is 7.2 on your test, we've got calcium has got 2 positive charges and the nitrate ion has got 1 minus charge. So to balance it out, we're going to need 2 of those nitrate ions. And because they come in sort of like packets with a nitrogen and 3 oxygens, what we do to distinguish that there's 2 around it is you put a bracket around the NO3, and then you put the little subscript 2 next to it. So it tells us we have 1 calcium and 2 nitrate ions. For 8.3 or 7.3 for you, it's a 6 marker. You don't need to hit every bullet point to get 6 marks, but what we're looking at is a set of instructions that are in the right order, that if you followed them would get you pretty much the right idea. They've not told you which metal oxide to use here. So if you went all the way through and just said, get the metal oxide and the acid and mix it together, you've missed the very first step. Okay, so we want to make magnesium sulfate. So the metal oxide that we need would be magnesium oxide. We want to make magnesium sulfate. So the acid that we're going to need is going to be sulfuric acid. So we can make magnesium sulfate. Okay, I wasn't going to give you 6 out of 6 for anyone that didn't say that. Then what you need to do is add your acid and your magnesium oxide into a container. You might have suggested warming it to speed the reaction or stirring it to speed up the reaction, and you wanted to try and make sure that you added excess magnesium oxide in this case. I was ignoring any references to it turning blue because this wouldn't turn blue, copper sulfate would, but magnesium oxide wouldn't. But you'd know it's in excess because it would no longer be disappearing. You'd have the powder in this case settle into the bottom. You'd then filter it using the filter paper and funnel, which would leave the solid magnesium oxide in the paper at the top, and then the solution would fall down to the bottom. And then to separate it out, you would look at some form of crystallization. Most people talked about leaving it on a windowsill or something, and the sunshine evaporating the water and leaving the crystals behind. Some people were talking about warming it over a Bunsen burner or a steam bath. Okay. For 9 then, I think it's your 8. Determine the formula. So the pattern here is we've got 1 black ion for every 2 grey dots of sulfur. So that's the ratio. If you added them all up and then simplified the ratio, or if you just looked at that pattern itself, it'd be FeS2. Obviously, that's got to be a capital F, a capital S, a lowercase e, and it's got to have that subscript 2. It's got to be in the right format. In terms of protons, neutrons, and electrons, number of protons is this bottom number, 26. The atomic number tells you how many protons there are, and obviously as you go across the periodic table, each step across increases the proton number by 1, so hydrogen 1, helium 2, lithium 3, beryllium 4. So it's the number of protons that determines the element. And it would have, for a pure element, the same number of electrons. That can change when they bond, so it's not always the number of electrons, but because this is just iron, the element, if you've got 26 positive protons, you'd have 26 negative electrons with an overall neutral charge. And then to get the number of neutrons, you might remember you get 56, and you subtract the 26 protons away from it, because the 56 is the total mass. 26 of that is the mass of the protons, so whatever's left, the 30, is the mass of the neutrons. For number 9.3, or this 8.3 for you, I think, it's comparing transition metals and alkali metals, and it's asking for two differences in the properties of them. So what we're doing here is we're ignoring stuff talking about electrons and atomic structure. We're talking about properties. So we want things like iron, and we need comparators here. You don't want to just say that sodium reacts. It doesn't tell me anything about sort of comparative between the two. So iron is harder or more dense or stronger, or iron is less reactive, or it's got a higher melting and boiling point. Can be used as a catalyst or is in coloured compounds, whereas obviously in that case sodium is not a catalyst or in coloured compounds. Those last two things are features of transition metals only. For 9.4, explain why carbon's used to extract nickel oxide. This is a Kim-Carnier reaction, if you know what I'm talking about there. So carbon is more reactive than nickel. You can say the opposite. So the carbon will displace the nickel to form carbon dioxide and leave nickel on its own. So carbon is going to take the oxygen away. So the two bits you want to be talking about there, it's saying carbon is higher in the reactivity series, please send Charlie's, monkeys, and zebras in cages securely guarded. And it's going to take the oxygen away. Here we've got a question asking for the percentage atom economy. So atom economy is looking at what percentage of the atoms went into the useful product. We're looking at producing nickel here. So if you look at the end, nickel is 59. So nickel is 59, and then that's out of a total of that 59 and the carbon and the oxygen. So the nickel, carbon, and oxygen all together gives a total of 87. So you'd have a mark, and I gave a lot of marks out for people who had an 87 there. And then you had to know that it's the nickel out of that. So it's 59 out of 87, and then it turns into a percentage just like you would for a test score. 59 divided by 87 times by 100. We're looking for three significant figures. So 6, 7, and 8 are your first three significant figures. Okay. Don't confuse it with 3 decimal places, because obviously that would lead you to 67.816. So you don't score 2 marks for that. It's worth noting you can get a wrong percentage there with given 3 significant figures in many cases. They allow an answer from an incorrect calculation to 3 significant figures. You can get a mark for doing an answer to 3 significant figures as long as you've had a good go at it. And we didn't do question 10 because you haven't done that bit yet. So I think that's the end of it. Let me know if I've made any mistakes. Do please ask if you've got any problems, or if you want to go over anything. This isn't done and dusted now. You've obviously got to try and retain this through to year 11. If you finish this video nice and quick before the end of the lesson, please do hop on to Seneca. If electrolysis was a problem area, go do some work on electrolysis. Use Oak National Academy or something like that. Set yourself some specific targets. Okay, look at the front now. Look at which question you scored the lowest on, and set that as a target. Now maybe that's something you do today. Maybe it's something that you do over the holidays. But like, you're weak in that area, so don't leave that until like summer term of GCSE year before you start combating that. Okay. Well done to you all. I'm super proud of the work that you've been doing this year. Thanks very much for your hard work.